The start of chapter 9, actually all of chapter 9, is going to feel very, very familiar to you guys. What we have to take a look at are some graphs of rational equations where we have asymptotes, vertical asymptotes and horizontal asymptotes. And even though this won't be crystal clear in your memory, if I say something like kitty corner, it probably pops back in of kind of the general ballpark of what we're taking a look at. So what we need to do right now is really push forward in the understanding of asymptotes and then something called the point of discontinuity in the next section. They are critical pieces of information for the start of limit studies, which is where you will begin your study in calculus. So let's just do a recap of what you saw in pre-calculus 20. If we were given the rational equation y equals 1 over x minus 2, and I'll start off by saying that in pre-calc 20, we always had a 1 up here. We actually called them reciprocal equations. We were just flipping things. It can be any number you want. It can be any variable you want up here. But what we'll do is we'll just start off comforting. We'll put a 1 there. And so we started this way. What we first of all said was you cannot have x being a value of 2. Because if you did that, 2 minus 2 is 0. You can't divide by 0. It's an error. It's a no-no. And then we realized that was what a vertical asymptote was. At x is equal to a value of 2. So if I just come out and put it down, the graph did not exist there. Now, here's something I asked you guys to memorize. The horizontal asymptote is always at a height of 0. And I said that all the way through pre-calc 20, and I stand by it. And then I said in pre-calc 30, we'll learn how to move them, which is actually today. So then here is our final thing. And this again should be a little bit of a trip down memory lane. When we take a look at this guy and we say, okay, what would the graph look like? What we did was we used the x-intercept as just a little bit of a cue. We looked at this and we said, sorry, I lied to you. There is no x-intercept. What would be the y-intercept? Well, if we subbed a 0 in for x, it virtually wipes it away. The y-intercept is negative a half, so somewhere about down here, and then I'll bring that x back in, and now we know. The graph comes from one asymptote, approaches another, and then it jumps kitty corner, and this was the graph that we looked at. It was quite pretty. The first time you saw it, you were left wondering, well, are we just making this up? And what I actually said to you guys is sub in numbers. Sub in numbers like 3, 4, 5, 6, and see a plottable set of points coming, or numbers like 0, -1, -2, and you'd see where these points are coming from. And this is the graph that we were studying. Now, to fill in some of the extras, here is what we would go with. The domain and the range, if we just started plopping down XER and YER, we are not correct, but we're not far off. This graph goes forever to negative infinity, forever to positive infinity, but it does not ever equal 2. So what we did right now, because we don't really have a better method, is we just said x will never equal 2. The range is every single number. We go forever up, then we go forever down, except y is never a height of 0. Now, here's where there's a little bit of a repeat. This is just to help you kind of see the big picture for moving into a study of limits in calculus, and we didn't do this in pre-calc 20. If we said, what is the non-permissible value? Well, x can't equal 2. It really is wrapped up into that vertical asymptote. And then if we talk about end behavior, there's two different ways that we could say it. So the very first one would be as you go to the infinities, negative infinity and positive infinity, as you approach either positive or negative infinity on the x-axis, we're going to a height of 0. That would be what you'd say is an end behavior. It's almost like saying what is the horizontal asymptote. And then there's one more version of end behavior that we're going to say, don't panic about these guys. Okay, they're just ways to try to see this in a little bit of a bigger light. The end behavior near the vertical asymptote. If we came flying in, okay, from the right side, and imagine you're going on a little trip. So just imagine we're going on this red graph, coming in from the right side, getting closer and closer to the vertical asymptote of 2, we are going to positive infinity. If we took a little road trip on this graph from the left side, imagine going on this red graph, and you got closer and closer to the asymptote of 2, we're going to negative infinity. Now you might be saying this end behavior is a little silly, stupid if you will, because you're just kind of stating the obvious. It's all right there in the graph, but they will be important details as you guys move into a study in calculus of limits. So let's go to our example number 2. And for example number 2, what I'm not going to do is fill in all these values. Once you come to grips with the number up top, which is really easy to do, then you guys can just read what example number 2 looks like. So here's what we're going to take a look at. And it's a very, very quick one. We have y, or in the PDF notes, f of x is equal to, and up top, we have a 2, and then the denominator is x plus 3, and we're supposed to, again, state everything. So here's how this guy unfolds. Number 1, we have a horizontal asymptote at a height of 0. And so you'd see y equals 0 in the notes. We have a vertical asymptote at -3. And so you'd again see that in the PDF notes, and the non-permissible value, you cannot be at x equals -3. So hopefully that's kicking in. The only point of this example was just to say it's a 2 there. It doesn't matter. In pre-calc 20, we always just had a 1 there again because we were just flipping things to get started. This can be any number you want. It doesn't change anything. We're still going to get a kitty corner graph. And how are you going to figure it out? Well, let's find the y-intercept. So let's sub in 0 for x. We got a 2/3. 2/3 is somewhere up here. I know it's a little bit funny, but that's where it's going to be. And now we can draw our graph and jump kitty corner. Sorry about getting so close over to the edge. And we could go through all of our different values. So the point of the second example was just to say don't panic on the 2. Now, the third example, and again, I'm going to not cheat or be lazy, but once you see the graph, I don't think that these are going to be the biggest deal, and you can read them in the notes. In number 3, we have a very simple graph, just y equals 7 over x. And you might be left wondering, well, what the heck is going on? How am I going to know what's going on? You, first of all, have to just stick to your guns. We are still in the horizontal asymptote, always being at a height of y equals 0. Now, where would the vertical asymptote be? What value could you not sub in for x? It's just a straight out 0. X could never be 0. There's no other number, and so it's so easy it can deceive you. So the vertical asymptote is at x equals 0. But then you might be left wondering, okay, how am I going to know the kitty corner? Our clue was always to figure out the y-intercept. Well, there's going to be no x-intercept because that's an asymptote. There's going to be no y-intercept. That's a vertical asymptote. It's either going to run here and then jump kitty corner or vice versa. How are you going to know? Just plot a point. And I think the point that I plotted in the PDF notes was I said just put 7 in for x. 7 divided by 7, sorry about that, you guys, is a 1. So if you were out here at 7, you're at a height of 1. Now I know everything I need to know what the graph looks like. Plotting a point can prove what's going on, but it can also just say, hey, here's basically what we're going to take a look at. And we could do it again. Let's say right here was 1 on the x-axis. Well, put 1 in for x. 7 divided by 1 is a height of 7. You can see this by plotting points, and then you could answer all of your different values that you'd be asked for. Now, I'm not rushing that just because I don't think it's important. It is very important. But I think what we really need to do is get to the new stuff. That is mostly old news for you guys. The new stuff, which comes immediately in our final 2 examples, is we can actually very, very easily move where the horizontal asymptote is. And it doesn't make it crazy. It just requires a few things to pay attention to. So here's our first out of the 2 examples. And there's a little bit of extras in the PDF notes that the person would have written down as we were going through this on the board. So here is our newest equation. And right away you notice a difference, but don't panic. It doesn't make the graph suddenly right crazy. What we have is y, or f of x, equals 4x plus 1 over x minus 5. And there is, first of all, one good instinct. What could x never be? X could never, ever equal a 5. That is where the vertical asymptote is. It's going to be at 5. So 1, 2, 3, 4, 5. But here's where the difference comes in. Because we have an x value here, the horizontal asymptote is not going to be at y equals 0. What you do when you have a variable top and bottom is you actually use the coefficients in front of the variable. So there is a 4, and it's assumed to be a 1 right there. That would be where the horizontal asymptote is, at 1, 2, 3, 4. That is the new part. Now here's where you guys are going to have just a little bit of faith with me. This right here, you could prove it in 2 ways. Number 1, you could just do an old plot a set of points to see that I'm not making this up. The truest way to prove it is with something called a limit, which you guys are going to have to wait for until you study calculus if you ever do. So then, how could you still figure out, well, what does this guy look like? Does it go kitty corner down here and jump up or vice versa? It still is the y-intercept. When you sub 0 in for x, it basically wipes all that away. The y-intercept is -1/5. So with a y-intercept of -1/5, now we know what this looks like. We know that it must come from this asymptote, go through our intercept and come down, and it gets a little bit ugly. It must come from this asymptote and go down. It's still jumping a classic kitty corner. So then the domain. The domain is all real numbers, but yet again we have an except. X could never ever equal a value of 5. The range is all real numbers, except y will never ever be a height of +4. Now the end behavior, I'm just going to say out loud, the end behavior, if we go to either positive infinity or negative infinity on the x-axis, you're approaching a height of 4. It's almost like you're just restating the horizontal asymptote, just like the non-permissible value is restating the vertical asymptote. And what would be the end behavior near our vertical asymptote? Well, if you come from the left, it goes down to negative infinity. If you come from the right, it goes to positive. I know it seems silly, but it is going to be something important. So then, with our final example, number 5, we see it again. We see how you can actually move your horizontal asymptote to be not zeroed, as promised in pre-calc 20. And so for our final example, we just simply have y, or f of x, is equal to -3x minus 1 divided by x, and then a plus 1. And we're supposed to, again, figure out what this graph looks like. And I'm going to start with what I think is the most obvious, the most comforting thing for you. You can never have x being -1 because that is going to be where there is a vertical asymptote. But unlike the old days meaning pre-calculus 20, the horizontal asymptote is not at 0 this time because you have a variable top and bottom. And again, you will see this proven with limits if you take a calculus course. What you do is you use the coefficients. Okay, so right now, same thing again. I'm just going to do a couple out loud. This is assumed to be a 1. So the horizontal asymptote will be at -3 divided by 1. So it'll be at -3. So we will go down 1, 2, 3, and we will put down where our new horizontal asymptote is. And I'm just going to throw a couple of random ones in. Let's say this was a +3 in the question. Well, then when you divide these, it would be at -1. Let's say the coefficient was actually a 6 in the question. Well, then it would be at -0.5. You're just going to divide the coefficients, and again, you will see this again in a calculus-based course. Then, how are you going to figure out what this graph looks like? We will do again the old intercepts. If I sub in 0 for x, it essentially wipes that away, and you're left with just -1/1. So at -1 is our intercept. Now I know it must come from this asymptote and approach the next, and it's still kitty corner for right now. And we have our graph. Now here's where there's a slight difference. And I can even write these down. I'm not trying to cheat, I'm not trying to do anything bad, but I'm just going to take all of this away. And here's where there's a little bit of a difference. We have always been using the y-intercept as an effective way to know the kitty corner without plotting points. And so the y-intercept was a -1. That's how we found this point. Here is something that's kind of interesting for our finish of this day today, a longer day. There is actually an x-intercept. There is an x-intercept right there. And how do you find x-intercepts? Well, now you sub 0 in for y, and we have to solve for x, but it's not as bad as you think. I love denominators in senior math. Why? Imagine timesing it up. When you times the x plus 1 up, it essentially just goes away. You are just left with 0 equals -3x minus 1, slap the 1 over, divide both sides by -3, and we have an x-intercept of -1/3. So that is doable now. And so here is the key thing. We're just reviewing our asymptotes. Everything in pre-calc 30 is just a tool for later on, and you honestly can't rule any of it out. They're all important little tools. The asymptotes are incredibly important to study the first out of the big 3 things in calculus. There's limits, derivatives, and integrals. Well, to study a limit, you have to really understand what asymptotes are, and then again, something called the point of discontinuity, which we'll learn tomorrow.